No one wants to do it today.
Evan does.
Greetings and welcome, friends. Today we are talking about adding and subtracting rational expressions. We've done a little bit of work talking about just the concept of adding and subtracting. I want to do a quick little recall. Double L, bam. What if I wanted to add the fractions 5/12 plus 4/9? Okay? 9ths. Now, you might be thinking about this and be like, do I just add the 5 and the 4 and the 12 and the 9 and I'm done? No, you would be wrong. We do multiply across like that, but addition requires a common denominator. And preferably, we desire the least common denominator. All right, so I immediately ask the question, what number does both 12 and 9 go into? 36. 3 would be a common factor. I'm looking for a common multiple, and that's why I definitely take the time to go over this. So now I could just say, oh, whatever 9 times 12 is a common multiple, and that's true, but it's not the most efficient multiple. In fact, that would give me some really big numbers, and I'd have to end up simplifying all my answers like crazy anyway. So no thank you. I'm going to look for the most efficient. So one of the ways you might think about that is by trying to figure out, right, keep multiplying 12 by, like 12 times 1, 9 doesn't go into it. 12 times 2 is 24, 9 doesn't go into it. 12 times 3 is 36, 9 does go into it. That's one way you could do it. Another way you could actually break these down into their prime factorization. I might show that technique in a second. So the LCD between these is 36. All right? And the idea is, I guess I might even write some steps. Step 1, find LCD. Step 2, multiply each fraction, top and bottom, by the part of the LCD it's missing. Which this language will actually make more sense, me saying part of, when we get to our polynomial stuff, rational expressions. A part of the LCD it is missing. And then lastly is, right, add or subtract the numerators. It just scrolled down, that's all. I was scared too, though. I was really scared. Whew. All right, add or subtract the numerators and put over the LCD, the common denominator. Right? And then I guess you could always simplify if possible, but that's hopefully obvious. So the question is, what would I multiply 12 by that would give me 36? 3. So I'm going to multiply top and bottom by 3 over 3. Now, why does it have to be top and bottom? Because that's the rule. Well, if I just multiplied by the bottom, that'd be the equivalent of dividing this fraction by 3, which is going to change its value. Multiplying top and bottom by 3, right? 3 over 3, that's the same as 1. Multiplying by 1 is not going to change it, right? It's just going to end up giving me something equivalent, because 1 is the multiplicative identity. Now, so multiplying by 3 over 3, it's not changing its value, it's just changing the way it looks. It's like if I go to a convention dressed up as Legolas, I'm still Brian Waddy, I just look different, right? That's what we're doing to 5/12. We're making it look different. I've never been to a convention dressed up like Legolas, just so you know.
What is that?
Because of course you all know I'm a huge fan of Gimli. But anyways, what would I multiply 9 by to get 36? 4. So I'd multiply top and bottom by 4. And notice 4 over 4, that's equivalent to 1. Multiplying by 1, it's not going to change the value. It just changes the way it looks. So let's do this. 3 times 5 is 15. 3 times 12 is 36. 36. Plus 4 times 4 is 16 over 9 times 4 is 36. All right, so this is mathematically unchanged. It's equivalent, hence my use of the equal sign describing its equivalency. So what do I do now? I add or subtract the numerators and put over the LCD. So what is 15 plus 16?
31.
31 over 36. Good call. And can this simplify? I don't think so. In fact, I believe 31 might even be prime. P-rhyme. So that is how we would have done that problem. Now, what do I mean by the part of the LCD it's missing? Well, in this case, I was kind of saying, well, what would I multiply it by to get 36? If I wanted to understand this language, I just want to point out that I could have viewed 12 as 2 times 2 times 3. Have you guys ever seen prime factorization before? I think so, right? I think so. And 9 is the same as 3 times 3. So check this. The LCD is going to actually be made up of these components. These are kind of like the little molecules that make up our numbers, right? The little atoms that they are composed out of. So the LCD is going to have at least as much of a number or factor as is represented in either of these. So the LCD needs to have at least 1 2. All right. In fact, it has to have 2 2s because that problem, 12, had 2 2s represented in it. Uh-oh. Let's see, my tablet just died on me. Just up and died, guys. Oh, I'm back. I'm back. Here I am. Haha. So 2 times 2 would have to be part of that. Now, how many 3's multiplied would have to be in the LCD, do you suspect? Do I just need 1? Do I need 2? Or do I need 3 of them?
3. 2. 5.
It turns out I only need 2. I only need as many as were most populating any of the individual numbers. All right, that's an ugly looking 3 there. And notice 2 times 2 is 4, 3 times 3 is 9, 4 times 9 is 36. So that is my LCD. If I included the other 3, what would that have equaled? 90 plus 18, 108. And that's what I would have gotten if I just plain old multiplied 12 and 9. So what I end up having is I calculate the LCD. Notice I only included as few as I could possibly, right, for each of these. So even if, say, this 9 was an 18, if there was like an extra 2 here, if this was an 18, I still only would have needed 2 2's. And now what do? I multiply each fraction top and bottom by the part of the LCD it's missing. What do I mean by that? This one has 2, 2, and 3. 2, 2, 3. Here's the part of the LCD it's missing. 3 over 3. Okay? I know this is not at all necessarily how you'd think about adding fractions. It is how we will think about adding rational expressions, though. All right, so I'm just trying to bridge some conceptual understanding. This one is 3 times 3 times 2. So notice I've got 2 3's and a 2 there. So what do I have to multiply? Oh, wait. Wait a minute. Oh, no, that 2 was not there originally. That was my fake 2, my phony 2. This one was 3 and 3, 3 and 3. So what's the part of the LCD it's missing? The 2 and the 2. So that's why I have to multiply by 4 over 4 for that. So let's keep going. So that's the general idea. Let's try an actual problem regarding rational expressions. So getting into the real stuff. Let's suppose I had 2x over 5ab cubed, Jacob, and I'm adding to that 4y over 3a squared b squared.
Yeah, I know. It's like a transformer. It's like you're in a car.
Yeah.
You're in a car, and then you transform into Bumblebee.
Well, this isn't actually even the hardest kind of problem we're going to do today. So I'm just trying to pace it out in some sort of linear progression where we have a learning curve that's not too crazy. But yeah, at some points this stuff is just plain old cray. Am I right, Hank? I'm right. So, all right. So the first thing I need is an LCD. Okay? Between 5 and 3, what's the smallest number that they both go into? 15. Skylar, what does your phone say about the LCD between a and a squared? So between a and a squared, the smallest thing those both go into is a squared. Right? And between b cubed and b squared, how many b's do I need? Do I need b to the 5th in the LCD? No, I just need however many were at most represented in a single denominator, right? So I only need 3 of those. So b cubed. So this is my LCD. All right? So now my question is, Joey, what do I multiply the first fraction by? The part of the LCD it's missing. So to get 15 out of 5, I have to multiply by 3. To get a squared, what do I have to multiply by? An a. And b cubed I already got, right? So b cubed we're good with. So I'm going to multiply this by 3a over 3a. Jacob, on this one, I've got the 3. I need 15, so I'd multiply by 5, right, to get 15. A squared I've already got. That one's good. And b squared, I wanted b cubed. So what do I have to do? Multiply by b squared times what is b cubed? B. So 5b over 5b. Top and bottom, just like the instructions we had a moment ago. Top and bottom by the part of the LCD it's missing. Right? So let's actually multiply these out now. So 3a times 2x, 6ax.
Wait, why don't you take it from,
Plus, let's see, 4y times 5b, that's 20 by. By. And now, what is 3a times 5a b cubed? Or what is 3a squared b squared times 5b? Hopefully it's this, if I did my work right? I mean, that better be what it is. Otherwise I was wasting my time. Oh my goodness. So one of the things I might let you do on your homework sometimes, I might just let you write LCD.
Really?
Yeah. Isn't that pretty cool? I mean, mathematically, if I already defined this very clearly up here, which you would have to, now I can use its shorthand notation, which, by the way, it's not that much shorter in this case, 3 symbols compared to however many there, 6 or 7 there. But sometimes the LCD is going to be like crazy long polynomial factors. So you can take that little shortcut for a little bit there. Now, I've got an LCD. What do I do next? What's the step say? Add or subtract the numerators, put it over the LCD. Let's see, 6ax plus 20by. Are those like terms?
No.
No. So I'm just going to write 6ax plus 20 by all over the LCD.
Why wouldn't you just go 26?
Oh, no, those aren't like terms. That's like saying 3x plus 4y is equal to 7xy. Muy illegal, right? I can only combine like terms if they have the same variables and the same exponents, right? So that's why I couldn't combine those. Now, I still wrote this over LCD because there's the potential of simplifying it. So I should actually now check to see if I could factor anything. I think I can. What could I factor out of this?
2.
Yeah, 2. Yep, I like it. So this is going to equal 2 times 3ax plus 10by all over, and I don't believe this is going to cancel out with anything, so I'm gonna just write my final LCD, 15a squared b cubed. Nothing cancels out, so I believe I'm done. But like if that 15 was reducible by 2, then I would have canceled out and done all that stuff.
No fruit ninja.
Yeah, no fruit ninjas in this case, but that's okay.
What about the 3 and the 15?
Oh, super illegal. Can't cancel that 3 and 15 because that 3x plus 10by is a single factor. The only thing it would cancel out with is if I had another 3x plus 10by over here. Then I could cancel those out. Okay? So our skills from the last section are still going to be in play here, but now we're throwing in the mix common denominators, adding and subtracting fractions. So it's going to be getting a little bit more complex. Let's try another problem. Pick it up a notch. Here we go. What if I've got x over x squared plus 5x plus 6, and I'm subtracting this time. Oh, I love it. I love it. 2 over x squared plus 4x plus 4. Now, I don't actually want to start analyzing the LCD until I have factored the denominators. Okay, because I don't know what those things go into together, right? Like I would just end up saying that a common denominator is this times that, but that's not going to be the most efficient. And in fact, it'd probably give me something that I would then no longer have the ability to factor without having to do a whole bunch of guess and check, rat root, Descartes, complex conjugate, sort of stuff like that. No, thank you, friend. So let's factor both of those. Let's see. And I'm not going to actually ever bother factoring the numerators at this point until after I've added them.
You never do that?
Yeah, correct. 1 and 6, 2 and 3. This is 1 and 4, 2 and 2. So what are those? Oh yeah, this is also a pattern. I like that. This is also the a squared plus 2ab plus b squared pattern. I like that even better. Either way would work. But let's factor these. So this denominator, I'm going to have an x with a 2, an x with a 3. This denominator, I'm going to have, we'll figure out those signs first. Plus plus, right? I think you guys agree. And this one I can factor to be x plus 2 all squared. So they're factored. Question, what is the LCD between those ones there? Now, how many x plus 2's do I need? I need 2 of them. All right, I don't need 3 of them. I don't need x plus 2 times x plus 2 times x plus 2. I just need however many are represented at most in a single denominator. So I'm going to have my LCD is x plus 2 all squared. How many x plus 3's do I need? Just 1, because there was one of them represented here. Even though it wasn't represented over there, I still need it. So this is my LCD. So now, what's the next step? Let's keep bringing it back to those steps. So when you're doing your homework, try to follow the steps. Look at your other examples as well. So it says, multiply each fraction top and bottom by the part of the LCD it's missing. Okay? So for this denominator, what part of the LCD is this missing? It's missing one of the x plus 2's, right? So I'm going to multiply this one by x plus 2 over x plus 2. What is x plus 2 divided by x plus 2?
1.
It's just 1, right? This is just like a big ugly 1 in disguise, right? It's just hiding. It's not changing the value, it's just changing the way it looks. Right? And what part of the LCD is this one missing? X plus 3 over x plus 3. So, let's multiply this out. Up top, I am going to distribute the numerators. All right, I am going to do that. The denominators I want to leave factored because the next step, once I combine these, the denominator stays the same, right? Like for the rest of the problem until I hit the simplifying step. But the numerators I'm going to have to combine. So let's see. So when I multiply this out, I guess I'll write those in blue. And we'll have x squared plus 2x over the LCD. Right? So you don't have to write out that whole thing. And then now we've got a choice. I could distribute the 2 and leave this as a minus sign. Or I could distribute this as negative 2 and make this into a plus sign.
No, keep it negative, minus.
Okay, you want to keep it minus? That's fine. Yeah, that's okay. We'll do that. We'll end up having to distribute that in a moment anyway. But it will still be valuable for us to see how that works. For subtraction problems. So I'd get 2x plus 6. Now, what do? I've got my common denominator. I add or subtract the numerator, put it over the LCD. So, in order to subtract these, I'm subtracting this entire numerator. Okay? The entire thing is being subtracted, not just the 2x. So that's actually going to change the signs of all of those. Okay? So I'm going to have I'm actually going to rewrite this. X squared plus 2x. I can actually write it all over one big LCD right now. It's going to be minus 2x and minus 6. Oh, I almost made the mistake I was just warning us about.
So it's x squared minus 6.
And now I could combine like terms. The two x's, they become friends but then kill each other in a fight. Oh, that's sad. So yeah, it's going to be x squared minus 6. Is x squared minus 6 factorable? Is that a difference of squares?
Yeah.
No, 6 is not a perfect square. And because that's not factorable, I'm actually going to write down the LCD this time. x plus 2 all squared. And
Why does it matter if you write it down? Just say after you.
well, because this is going to be my final answer. So my final answer actually should be, man, I'm getting bad lag. Here we go. Ah, whew. Goodness. I wonder if I can close anything down on my computer. Not really. So can I cancel anything out?
No.
If I could, I would have to. If the numerator was factorable, I would factor it and see if it could reduce, just like we did on like previous, homeworks with multiplying and dividing. So let's look at one last example, and we're going to be good for today, I hope. You want, what do you say, 2 more examples?
No.
We can do it!
No.
Oh, okay. No, we'll just do one.
No.
X minus 5 over 2x minus 6 minus x minus 7 over 4x minus 12. And before I find those LCDs, I want to make sure those denominators are factored.
If you take it to
Yeah, it looks like a GCF in both of them.
4.
Right? Do you guys see that? So when you're doing your homework, don't just be like, I don't know where to start. You have to look at other examples. You have to follow the steps. Right? You guys can be clever like that. So 2 times x minus 3 here. And this is what? 4 times x. Oh, hey. That's not that bad.
Okay.
They're sharing the x minus 3s. They're buddies. So,
Wait, wouldn't it be 2 x
I'm stealing a 4 out of that.
Oh.
An entire 4. So what is the LCD?
2.
Between 2 and 4, what number do both of those go into? 4. 4 goes into itself, and 2 goes into 4. So I need to have at least a 4 in the LCD. And how many x minus 3s do I need? Just one of them. So let's multiply each of these by the part of the LCD that it's missing.
2.
What is this one missing? This just needs to be doubled, right? So multiply top and bottom by 2. What's this one?
1.
That one's already got the LCD. That's good. I don't need to multiply that by anything. If you wanted, you could say 1 over 1, but let's not even change it. Now, another common place for mistake is when people multiply a numerator that's a polynomial by something, they don't distribute, okay? Remember, this vinculum is a grouping symbol. You could literally think of every numerator and denominator here as having been in parentheses, okay? So when I'm multiplying this numerator by 2, that entire numerator is being multiplied by 2. Don't just multiply the leading coefficient by it, okay? So that's going to be 2x minus 10 over the LCD minus x minus 7 over the LCD. And I know you guys are not going to fall for the subtraction error there as well. Once again, this vinculum is a grouping symbol. I'm going to have to distribute this minus sign. You could have, done those 2 previous steps as one, and that's fine. But I don't mind having us have it written all out in our notes. So let's see, 2x minus 10 minus x and plus 7 all over the LCD.
So
Combine like terms.
x minus 3
X minus 3 over,
4.
I can't factor the numerator any further.
Can you cancel?
Can I cancel this?
Oh,
No. Can I cancel this? No. But I can. Whooshing, whooshing. That's right. An x minus 3 cancels.
4?
Nope.
1
What's-
over 4.
1 over 4. I like it. Yeah. So who would have thought when you were subtracting those 2 things that was just equal to a quarter? What do you know? But that's the idea. Factor the denominators. Find the LCD. Multiply each fraction, top and bottom, by the part of the LCD that it's missing. All right? Then you can add or subtract the numerators, put them over the LCD, and then simplify as you normally would. All right? That's the idea. That's today's lesson. Under 25 minutes. Enjoy. Ba-bam.